Right before your eyes is one of the most dangerous roads in India, where heavy trucks struggle to maneuver and make way for each other on a surface exactly 5 meters wide. On one side is a precarious cliff with loose rocks that could fall at any moment, and on the other side is a vertical drop of hundreds of meters. This is the original Char Dham route, located deep in the Himalayas. It serves as a vital traffic artery, handling the entire logistics supply chain for the region. But currently, the traffic volume here has exceeded its design capacity many times over. To solve this infrastructure bottleneck, engineers had to undertake a highly complex task, widening the road's cross-section from 5 meters to 10 meters to meet the standards of a 2-lane national highway. However, the Himalayas are a region of geological faults. Using heavy machinery to cut 5 meters deeper into the base of the cliff means breaking the center of gravity of the entire mountain mass above. A mistake in calculations could instantly cause millions of tons of rock to slide down. So, how did the engineers carve into the mountain to widen the road without collapsing the geological structure, while successfully building half of the road extending right over the deep abyss? Let's find out in today's video. Before we begin, don't forget to leave a like and hype up this video. Now, let's get started. Conquering 900 kilometers of Himalayan terrain is a puzzle that cannot be solved with a single formula. This massive workload had to be broken down into 53 independent mechanical bidding packages, applying zoned geotechnical planning based on specific geological features. Where the mountain core has major fault structures, engineers excavate mountain-piercing tunnels using the new Austrian tunneling method, or NATM. Where valleys sink, a network of viaducts is established by driving a system of drilled shafts directly into the cliff, extending the road surface away from the edge. However, tunnels and viaducts only solve the surface of the problem. Most of the project's length falls into a severe spatial limitation: 90-degree vertical quartz cliffs, where the mountain core is not thick enough to dig a tunnel, and there is absolutely no bottom space to build viaduct foundations. This is the harshest construction segment that we will analyze. At this geotechnical bottleneck, engineers were forced to deploy the most complex construction method, cutting 5 meters directly into the vertical cliff, while maintaining absolute mechanical stability for the entire mountain mass above. To do this, the first mechanical process is activated: treating hard rock cliffs. The basic rule when dealing with a vertical cliff is to prevent the spread of vibrations. If a large amount of explosives is used in the traditional way, the rebounding shock waves will crack the rock structure deep inside the mountain, triggering a massive landslide that would bury the entire construction site below. To widen the cross-section without destabilizing the bedrock, controlled blasting technology is applied. The process begins by using hydraulic drilling machines to create a series of parallel boreholes with precisely calculated diameters and depths along the target cutting boundary. Explosives are loaded into these locations at a low density, but the core factor determining success or failure lies in the Delay Detonators system. Instead of detonating all at once, the detonators are set with delayed times varying by milliseconds. The physical mechanism works like this. The first explosion is triggered at the outer edge, breaking the outermost layer of rock to create an empty space. Immediately, the explosions in the following milliseconds push the inner layer of rock to crumble into the newly created void. This chain ignition sequence completely absorbs the explosive force and cancels out the shock waves echoing into the mountain. The upper cliff remains intact, while the road width is precisely expanded by 5 meters. After the delay blasting process is complete, excavators clear the site, revealing the newly cut cliff. However, the rock surface now has many micro-cracks. If left untreated, groundwater will seep in and reduce mechanical friction, causing the rock layers to break down and separate. Engineers must immediately proceed with the second process, reinforcing and locking the cliff. This stage is carried out using the rock bolting technique. Specialized hydraulic drills create a series of holes perpendicular to the cliff face, penetrating 10 to 15 meters deep into the mountain core. Then, high-strength steel bars are inserted into these boreholes. To lock them in place, a cement grout mixture is pumped directly into the borehole under high pressure. Once the grout hardens, this steel anchor system creates an underground binding force, tightly pulling the cracked surface rocks to adhere to the solid bedrock inside. The mechanical principle of this process is entirely similar to the NATM tunnel reinforcement method. I will leave a specialized analysis video about this technology on the screen and in the description box, so if you are interested, don't miss it. Returning to the project, to complete the current cliff reinforcement process, high-pressure concrete spraying technology, Shotcrete, is deployed to protect the outer surface. Workers lay out a welded wire mesh system tightly against the entire area of the newly cut cliff. Next, hydraulic spray guns shoot the high-strength concrete mixture directly onto this mesh. The concrete layer sticks firmly, completely sealing all gaps, creating a solid reinforced concrete covering structure. This structure absolutely prevents the intrusion of groundwater and ensures long-term stability for the entire cliff above. The inner rock wall has been securely locked by a reinforced concrete membrane. At this point, the project enters its next mandatory infrastructure phase, constructing the final road surface. To ensure this new transport corridor can withstand the immense dynamic pressure from parallel convoys of super heavy trucks, a high-standard multi-layer paving process is activated. Initially, the entire dirt subgrade is graded by heavy machinery and statically compacted by super heavy rollers to eliminate underground settlement. Once the subgrade is stabilized, a high-strength geotextile layer is fully spread across the surface. This polymer material acts as a mechanical separator, preventing underlying mud from rising and compromising the structure, while simultaneously increasing the underground tensile strength for the entire roadbed. Directly above the geotextile membrane, heavy machinery lays down an aggregate subbase layer. Graders define the thickness, clearing the way for a fleet of dynamic, vibratory rollers to operate continuously. Under tens of tons of pressure, the stones are tightly interlocked, creating a solid, shock-absorbing cushion that distributes compressive forces from the tires evenly down to the bedrock. Finally, paving machines lay down a layer of hot-mix asphalt. Pneumatic tire rollers and steel drum rollers immediately follow, continuously compacting the surface while the asphalt is still at a high temperature to rigidly lock the material. This cycle creates a flawlessly smooth transport corridor, one that not only boasts extreme load-bearing capacity, but also acts as a comprehensive waterproof shield for the entire underlying foundation structure. As of 2026, the Char Dham Highway Expansion Megaproject has completed over 75% of its construction volume across a total length of nearly 900 kilometers. The vital arteries heading towards Kedarnath and Badrinath have almost reached the 99% finish line, completely reshaping from a narrow mountain pass into a standard transport corridor. However, the actual construction process is still facing many challenges. In the segment heading to Yamunotri, progress has only reached about 57% due to the complexity of geological fault zones and the risk of underground landslides. This proves a reality. Carving through mountains to build roads in the Himalayas is a technical puzzle that requires a lot of time to solve. Nevertheless, the core achievements reached so far do not come from the arbitrary use of mechanized equipment. It is the precise combination of heavy machinery and micro-geotechnical calculations. By controlling the delayed blasting sequence, applying high-strength rock bolting technology, and building gravity gabion foundations, engineers have step-by-step successfully managed the most complex geological structure on the planet. If you find these technical analyses useful, leave a comment about the next megaproject you want us to dissect. Also, don't forget to check out the in-depth analysis video I have linked in the description below. Hit like and subscribe to the channel so you don't miss new content. Thank you for watching, goodbye, and see you in the next engineering analysis videos.